Okay, started this first one. So we did a little bit of factorial stuff a few days back, and so I want to review that with a variable in there, like the n. So if you had 2n plus 2 factorial, right? Remember, factorial means starting with that value, and then you multiply by 1 less than that, and then multiply by 1 less than that, and then multiply by 1 less than that, all the way down to 1. Okay, so when you have a variable in there, like 2n plus 2, then that would mean 2n plus 2, that quantity, times 2n plus 1, right? It's got to be 1 less, and 1 less than 2n plus 2 is 2n plus 1, right? It'd be 2n plus 2 minus 1, 2n plus 1. And 1 less than that is 2n, and 1 less than that is 2n minus 1, and on and on and on, right? And we don't know how many of those terms it would be because we don't know what n is, but we know it would go on and on in that pattern down to 1. And then 2n plus 4, likewise, would be 2n plus 4, 2n plus 3, 2n plus 2, and so forth and so on and on and on. Okay, so now to simplify that, what would you do? Starting here, these would cancel. And so therefore, even though, and this is this whole kind of concept of infinity, like we talked about with the hotel problem and all that stuff we don't know, and it goes on forever and ever. However, what we do know is that up on top, each one of these terms, there would be a corresponding term that would cancel all the way forever and ever, and they would be gone. And basically your final answer would be what? 1, yeah, don't forget the 1 on top. 1 over 2n plus 4 times 2n plus 3, right? I mean, that would be your final result. Okay, so you guys try these last two right here real quick. Now, little hint on number 2, there is not parentheses around the 2n. In case your eyesight's not all that good, I'm telling you there are not parentheses around the 2n. Okay? All right, go ahead and try those two. Number 3, in the bottom, there are parentheses around the 2n. Right? So those are different. The top of number 2 is different than the bottom of number 3. All right, here we go. What's your answer for number 2? What's your answer for number 3? Perfect. Okay? So 2n factorial means 2 times n factorial. Okay, so n factorial would be n minus 1, n minus 2, n minus 3, on and on. The bottom be n minus 1, n minus 2. These would all cancel. And we'd just be left with 2. And then 2n plus 1, much like we saw up there, is basically from 2n on down. Those would all cancel, and you'd be left with 2n plus 1. Okay, so some little facts about it. But it also plays into what we talked about with recursive formulas. The next term, you got a sub n, and then a sub n plus 1 is the next term, and n plus 2 is the next, and n plus 3 is the next, and so forth. Okay, questions on the homework?
107.
107. Okay, on this section, we're finding these patterns and we're writing the sigma notation for those. So 3, so you got, read that to me, Jack. 3 minus 7.
Okay. 3 minus 9.
3 minus 9, thank you.
Plus 27. Minus 81. Plus 243. Minus 729.
That's it?
Yeah.
Okay, those 6 terms. Okay, so basically what you have is a sequence that you need to find. So when we write the sigma notation, right in here is the nth term formula that we practiced writing yesterday. So basically what you have is a sequence. It's 3, negative 9, 27, negative 81, 243, and 729. And you're adding those up. And so this is 3 plus negative 9 plus 27 plus negative 81 and so forth, right? So you treat those minuses as negatives on those numbers. So we're trying to find a pattern. Well, what are we doing? We're repeatedly multiplying by 3. We ignore the negative. Well, we don't ignore it, but we put that in as this, right? Negative 1 to the what? N plus 1. Now we talked about how you could just put that in as a negative 3 because you're multiplying by negative 3, then multiplying by negative 3, multiplying. So we could do negative 3 raised to a power and make that work as well. But I like when you have alternating negative, just take that out of there. Just make that separate. And so this would be negative 1 to the n plus 1 or n minus 1, right? Either one, because that will be an e. Now I'm assuming we're going to start, now I used an n there. Usually we put an I, to be honest with you. Let's do an I. It could be an n. We could do n there. That'd be fine. Usually in this notation we do an I though. And I equals, and Caleb, when you start a sigma, this always has to be what here? A whole number, right? That can't be a fraction or a decimal. That's got to be a whole number, right? Now, we'd like it to be 1, and most of the time I would start that at a 1, but we could start it at something else. But usually our default is to start it as a 1. Okay, so if you put a 1 in for I, that'd be negative 1 squared, which is positive, and then a 2 in, negative 1 cubed, that's negative, and there you go. Okay, and then we're repeatedly multiplying by 3, so that would be 3 to the, now we want to get 3 on our first one, so we need 3 to the what? 3 to the first, right? Oh, that's good, because I is a 1, so that makes it easy. So it's 3 to the first, and so that's 3 to the I, right? So it'd be 3 to I would be a 1, so that'd be 3 to the first, I would be a 2, that'd be 3 to the second, that's 9, I would be a 3. Okay, and then it goes to where? Well, if I is a 1, 2, 3, 4, 5, 6, okay? And it'll always go by ones, it'll always go up, and it'll always be positive numbers, whole numbers, positive integers, okay, where it starts and where it ends, okay? And that'll do it. That will generate this sum, and you can test it, put a 1 in, negative 1 squared is 1, times 3 to the first is 3, okay, put a 2 in, negative 1 to the third is negative 1, times 3 to the second is 9, negative 1 times 9 is 1. Okay, got it? Jack, that answer that? That helps. Okay, what else? What else? What else? Anything?
How do you add the sum of an infinite series again?
Okay, so are you talking about 117 and 119?
Yeah.
Okay, you start writing it out. So if you look at 117, 117 says the integral of, what is that, 6 times 1/10 to the I, so I equals 1 to infinity. And it says 6 times 1/10 to the I, is that right? Okay, so you just start expanding it. So what you want to do is you want to start expanding it and you want to check a pattern. So you put a 1 in for I. So whenever you have something like this, you want to expand it, you want to find the sum. The good thing is to write it out, expand it out. So put a 1 in for I, so we get 6 times 1/10, I'm going to use decimals. Okay, put a 2 in there, 1/100th times 6 is 0.06. Okay. Put a 2 in for I is 1/1000th, okay, and we start seeing the pattern, right? And so now we're going da-da-da-da-da. Okay, there's only special series that will, that you can add up infinitely, right? Like if you did 1 plus 2 plus 3 plus 4 plus 5 forever and ever and ever, right? Just keep getting bigger and bigger and bigger. You're adding up bigger and bigger things. It's just going to go to infinity. We actually say that a series like that diverges, okay? However, one like this, we say converges. It converges to a single number. I got some little videos, little YouTube videos we're going to watch later in the week that talk about these kind of patterns. But when you start adding this up, what do you get? 0.6, 6, 6, repeating, right? Which we know is equal to what? That's equal to 2/3. That's equal to 2/3. Okay? And so that sum, so, you know, it seems strange, but that you can literally, you can take an infinite number of things and add them up, and it will equal 2/3. Okay? All right. So, but it takes special ones for that to work, for that to happen. Okay? And those are the ones we'll be looking at mostly here to start with. Okay? Well, one of the videos that we're not going to watch, I was just looking at, is one like this. Let's say S stands for a sum, and let's say we're going to add up an infinite number of things. What do you suppose 1 plus a half plus a fourth plus an eighth plus dot, 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 forever and ever, what do you suppose that would add up to? Just think about it. 2. Why do you say 2?
Because it keeps going halfway until eventually it has to be bigger.
That's the thing we were talking about to the doorway, right? If you stand right here, go halfway, then you go halfway, then you go halfway. Think about this. This is something we're talking about, partial sums. Think about the sequence of partial sums. In other words, let's start adding it up. 1 plus a half is 1.5, right? Plus a fourth, what's that? 1 3/4. 1 3/4 plus an eighth.
7
Would that be 7/8? That'd be 1 6/8 plus 1/8. It'd be 1 7/8. Then you would add on a 16th. 1 15/16. You see what's happening? And then it'd be 1 31 32nds and 1 63 64ths. You see what's happening? That fractional part's getting closer, that fractional piece getting closer and closer to 1. 63 64ths. You know, it's like 0.99 something already. Right? It would just keep going, it's getting closer and closer and closer to 2. And so eventually, it would be 2. Now, here's a cool little proof of this. Let's take this sequence right here. This is kind of like where we were dividing these factorials out here. Okay? Even though we can't go out to infinity, we can see a pattern. So let me multiply this by a half. Let me take this, both sides of this, and multiply by a half. So I'm going to multiply this side by a half, and I'm going to multiply this side by a half. If I multiply 1 by a half, what do I get? 1/2, right? Plus, multiply this by, I'm just going to distribute, right? I'm going to multiply this by a half, so multiply this by a half. Multiply this by a half. Oh, you see what's happening, right? Plus, dot, 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 dot. Now, let's do a little magic. Right? So this would go forever and ever and ever, okay? Now, let's subtract. What's S sub n minus 1/2 S sub n? 1/2 S sub n. What do we get when we subtract here? Cancel, 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 right? Subtract out forever and ever here. Okay, we get 1. Multiply both sides by 2. Right? So this sum up here has to equal 2. Right? Has to equal 2. So this, again, we can see the pattern. We can see it happening. But we can see it by that little bit of coolness. All right. So, any more homework questions? 111. Okay. So 111, looking for the pattern. Okay. So 1/4. 1/4. Read that to me. You got there at 3/8.
3/8, 7/16, 15/37, and 35/64.
And we're supposed to put that into a sigma. Right? Okay, so remember, when you put it in a sigma, what goes here is the nth term formula. We practiced that the other day. The plus part of this is just the sigma. Sigma means sum, right? So just pretend they're commas here, right? Just like we were doing earlier as a sequence. Just pretend they're commas, and we're going to write the nth term formula. So remember, n is 1, 2. That's where we usually like to write it. Now, technically, we'll call it an ith term formula because we'll start I to be a 1 here. Well, what do you see on here? You're repeatedly multiplying. Just look at the bottom like we were doing the other day. You're repeatedly multiplying by 2, right? Repeatedly multiplying by 2. So therefore, you think what? 2 raised to the I, right? problem is, if I starts as a 1, this will be 2 to the first, and we wanted 2 to the second. So what should we do? Let's do an I plus 1. Now, we could have started I here as a 2, right? We could have done that. We could have started I as a 2 and made this 2 to the I. That would have been fine, okay? It would have worked. You know, technically, if I give you this on the quiz and tell you to write a sigma, there would be an infinite number of sigmas we could write that would work, right? We could start I at 1 and have this be 2 to the I plus 1. We could start I at 2 and have it be 2 to the I. We could start I at 3 and have it be 2 to the I minus 1, right? You know what I mean? We could just go on and on, okay? Typically, we started at 1 and then make the adjustment. Okay, so that's going to give us the bottom. What's going to give us the top? What's that? No, I'm sorry. Yeah, up here, we'll get to that in a minute. But I'm at the top of the fraction, yeah. What do you notice about those numbers? Yeah, they're just one less. Remember, I think we said this. If you're adding up, if it's increasing by an increasing odd amount, we talked about that was a squaring situation. When it's going up by an increasing even amount, 2, 4, 8, 16, that's a 2 to the n pattern. That's the same thing as a 2 to the n pattern. Okay, this goes up by 4, then 8, then 16, right? So, or a doubling amount, excuse me, not an even amount, a doubling amount, 2, and then 4, and then 8, and then 16. So it's going up by a doubling amount. That's doubling, that's 2 to the n. So it seems to be one less than, except would it be I plus 1?
No.
It wouldn't be, it'd just be I, wouldn't it? So 2 to the I, so 2 to the first is 2, but then take away 1. 2 to the second is 4, take away 1. 2 to the 8th, 2 to the third is 8, take away 1 is 7, okay? So it looks like something like that. Now when you write this, be careful, because sometimes on a quiz people will write this, okay? Now what is that? Is that 2 to the I minus 1? Or is that 2 to the I minus 1, or you're not sure which one, so you're going to try to fool me. Okay? So, yeah, so usually then that'll be checked. Okay? What's that? No half a point, no. So make sure you're careful with how you write those powers. Okay? Whether it's up in the power or not. Okay, and then finally up here, what's this number going to be? This will be 5. That's another nice thing is if you start at 1, then this top number will always be, like Noah said, how many terms there are, right? It'll be how many terms there are. But if it's not, if you don't start at 1, if you get one that says I, and we're going to do this here in a little bit, if you get I equals 4 to 10, how many terms is that?
7.
It's good. It's 7 terms, right? 10 take away 4 is 6, but you're forgetting the first term, and so it's actually one more. Just like here, if you do 5 minus 1, that's 4, but there's actually 5 terms, so one more. If you subtract those and add 1, you get the number of terms. You could also say, well, we start at 4 instead of 1. That's a difference of 3, right? So that's 3, so that you take off 3. So you could look at it that way too. Or you can count on your fingers, 4, 5, 6, 7, 8, 9, 10. Okay, whatever. Okay, a little harder if I starts at 27 and goes up to 492. You know, it's a little harder to count on your fingers then. Okay. Anything else? Okay. All right. Let's get some notes down here about this. The next thing we're going to do with these sequences. Yesterday I talked to you about 2 types of sequences that we're going to focus in on a lot of our attention. And the first one is called an arithmetic sequence. Okay. So, and we're going to talk about sequences and partial sums kind of at the same time. Okay, so a sequence, remember, is with commas in between, and a series or a partial sum is when you're adding up the terms of a sequence. Okay, so an arithmetic sequence is a sequence in which consecutive terms have a common difference that we call D. Basically, in ordinary language, if you're adding the same amount to every term, or to go from term to term, that's an arithmetic sequence. Okay? So, add 2 to every term, add 3 to every term, add a -1, or you might say subtract 1 from every term. That's arithmetic. Okay? So it's kind of in a class by itself when you have one of those. Now, seems obvious, but sometimes if you get into decimals or fractions or something like that, it's not quite as obvious. It's easy when you get one where you're adding 2 every time, right? That's easy to see. But what if you're adding 3/5 every time? You know, I mean, sometimes that's not as obvious. So what you can do to figure out the common difference is just take the second term, subtract the first term. Take the third term, subtract the second term. Take the fourth term, subtract the third term, and on and on. Okay? D, so D can be positive. So if the sequence is going up, D is positive. If the sequence is going down, if you're subtracting, then D is negative. Okay? It's important that you know that. Okay? Because sometimes the question will be, what is D? What is the common difference, right? And the answer might be 3, it might be negative 3. You got to have the right sign on it. Okay? So that's the easiest way to check if you're not sure if something's an arithmetic sequence, is just take several of the terms and subtract the second minus the first, the third minus the second, fourth minus the third, fourth minus the third, and see what you got. Okay? All right. So here's a couple of examples. So the first one, 7, 11, 15. How much of this you write down is up to you. Look, 7, 11, 15, 19. Very obvious. You're adding 4 every time. Okay. Now, sometimes you'll see a sequence written this way where it'll be dot, 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 and then 4n plus 3, dot, dot, dot. They kind of sneak the nth term formula just right in there. Okay, and that would be the nth term formula. We practiced these. We said if you're repeatedly adding 4, that makes you think 4 times n, and then you would make an adjustment. 4 times 1 is 4, but we want 7, so we would add 3. So it would be, it's not hard to come up with that nth term formula. We've been doing that. Those are the easiest ones we did, really. And then I just, as a check, what I did, okay, 11 take away 7, yeah, 4. 15 take away 11, yeah, 4. 19 take away 15, 4. Okay, that's good. That's our common difference. Okay, another thing is, if we thought of these as a graphing situation or as a function, remember when we first identified sequences, we talked about them as functions, where the domain was 1, 2, 3, 4, and then the range, the output, were these numbers. If you graph this, this would be a line. And what would the 4 be? Slope of the line, right? And it's rate of change. Think about it. It's the rate that these terms are changing. Every time I go over 1, I go up 4. Over 1, up 4. Over 1, up 4. Right? The common difference in an arithmetic sequence is the slope of a linear function. There is that connection. We're going to see that connection again here in a little bit. Okay? Now you got one here where you're subtracting 3 every time, or excuse me, 5 every time, or adding a negative 5, you might say. But again, here's where you want to get D, and you want to make sure you get the right thing on here. Just take negative 3, subtract 2. Oh yeah, that's negative 5. Take negative 8, subtract negative 3. Oh yeah, that'd be negative 5. Take negative 13, subtract negative 8. Yeah, that's negative 5. Okay, so D is negative 5 in this case. And when you make your adjustment, you know, for your nth term formula, it'd be negative 5n plus 7, or could be written 7 minus 5n, whatever. Okay? All right, so nothing too new there. All we've done is kind of given some terminology, some vocabulary to a sequence we've already been seeing. Okay? It was really one of the easiest sequences we've been seeing. All right? And it's called an arithmetic sequence. All right, so we're going to come up with a little formula. You don't need to write this part down. But so if you think about then, again, to use some more vocabulary here, so think about this. So A1 is A1. That's our first term. A2 would be A1 plus D. Would you agree with that? D is the common difference, right? And A3 would be A1 plus 2D, right? If D is 4, if the common difference is 4, to go from term 1 up to term 3, you would have to add 4 twice, right? And term A4, you would do A1 plus 3Ds. And A5 would be A1 plus 4D. You start seeing a pattern, right? So A sub n could be written as A1 plus, not quite, is that n? That's n. It's n minus, seems to be n minus 1. Well, that makes sense, because A1 is our first term, and to get every term after that, we add on 1 fewer D's than where we're at. So if we want the second term, we just add on one D. If we want the third term, we add on two Ds, one less than the term we're looking for. If we wanted to find the 100th term, we would add on 99 Ds. So if the D was 4, you wanted to go from the first term to the 100th term, you would just have to add on 99 times 4, and then add that on to your first term, and that would give you your 100th term. Make sense? All right, so this is a nice little formula then that we have. Okay, this is our nth term formula for arithmetic sequences. Now, it's, memorize it. That's fine. I don't know. I haven't decided if I'm going to give you a formula sheet on these things. I always say that, and then I always end up being too nice.
Yeah, you have to do it for the one you forgot.
Except the quadratic formula. Jeez. Well, yeah, and then there wasn't one. I forgot.
Yeah, I was thinking for the people that came in the morning.
Yeah.
So
But see, you didn't even need it. You didn't even ask. You didn't need it. But anyway, so that's just a nice little formula that we could use in a lot of ways. For example, if we knew a certain term, or if we knew the first term and we knew the 10th term, then we could put that there. We could put the first term there. We could put a 10 in there. We could figure out the common difference. Or if we knew, so we got like 1, 2, 3, 4 variables in there. If we know 3 of them, we can find the missing one in an arithmetic sequence. Now, most of the time, it's pretty easy. We wouldn't have to use this, to be honest with you. You just kind of figure it out with some common sense and a little bit of calculator work. Wouldn't be bad at all. But this formula does work. Okay, so now, what could that look like? So, in other words, I want to show this 2 ways, and I don't care if you write this part down, but I just want to make that connection back to being a linear situation. So one way of looking at this is, okay, a sequence, 1, 2, 3, and then we got our different terms, and then there is our nth term. Okay? Now, I don't know why I'm using this screen. But, so now let's look at this part. So now let's look at it as a function. Let's look at it as an XY table, right? And so our X's are 1, 2, 3, 4, 5, just like here it's our 1, 2, 3. Then our outputs are terms, A1, A2, A3, and so forth. Okay? Now, this is the point slope form. We used it earlier in the year, right? This is a point slope form of a line. We got our slope here, X minus any old X point you want to pick, and then plus the Y point that goes with that X point. Okay? So that's just point slope form of an equation. Well, let's look at this. Well, first of all, to get our slope, we would just subtract a couple points. So let's take these first 2 points here and let's subtract them. Now, what's A2 minus A1 in an arithmetic sequence? Say it again.
D.
That's D, right? Same with A3 minus A4 minus A3 or A3 minus A2. A2 minus A1 is D. Okay, and what's 2 minus 1? Oh, 1. So, look at that. Our slope is D. We already said that. Right? Our slope is D. Okay, makes sense. So now if I want to write this equation, okay, since substitute in place of M, let's substitute D, okay, and then we would have X minus our X point. Let's just take this as our first point right here. So it'd be X minus 1 plus,
Mr. Clark, how are you doing?
I'm good.
What
Nice
are you
shirt.
learning about today? I'm guessing about today.
Nothing. Yeah, don't even ask him. Don't even ask him.
Huh?
Arithmetic sequences.
Oh, good.
Now you say it.
Good job, man. Way to go.
Nice.
Nice shirt, Mr. Marshall.
Geometric sequences too? Those coming up?
Yeah.
No?
That's tomorrow.
Okay.
Mrs. Payne, so they'll understand.
When do we get to start playing Pictionary? Oh, sorry.
That's calculus, but they probably haven't signed up.
Understand it's a lot better when you teach it, honestly.
Oh, jeez. All right, but
Martin filled that shirt out a little bit.
he just fills it out. He just fills it out different places. All right, so you got. I think we both fill it out. It just, Yeah, I was going to say the same thing, but whatever. All right, I don't know. I think a lamb or something. Is there something wrong? It was a mistake in the table. All right, so what would go right here? What would go right here? The Y point that goes with 1. A1. Oh, look at that. Okay, well look at this. Now look at that. It's the same thing. Just rearrange the terms here a little bit. You have A1 plus X minus 1 times d. Same thing, right? So this little formula for arithmetic sequences, the terms of an arithmetic sequence is no different than the linear equation, right? Y equals mx plus b, basically. Okay, so understand that kind of connection. It's a linear relationship. All right, so let's do a few examples here. So find the nth term of an arithmetic sequence whose common difference is -4 and first term is none. Go. Your answer will have n's in it, right? Find the nth term is like saying find the nth term formula, right? Okay, how are you going to start here?
I guess adding a -4.
So write it out. Okay, so one way to do it is just get it in the form that we've done before. So the first term is 9, and the common difference is -4. So the first term is 9. What's the next one? What's the next term? 5. And the next term? 1, right? Just write it out, and then do what we've been doing. Right? What? Yeah, we're making this. I see what you mean. You understand it way better than when Mrs. Payne explained it. Okay, so common difference is -4, right? And that's the thing you add on. Remember, the common difference is a thing you add on to each term. So the first term is 9, then 5, then 1, and then you can do this. Or we just learned a formula. We just learned a formula for the nth term. Okay? That's what this is. This is the nth term. That's what this formula is up here. Right? So you can do that. So you got two choices. So you can write down 9, 5, 1, -3. You can say, oh, you're adding -4 every time. So that means multiply by -4. So you do -4n, make an adjustment. So if the first term is 1, -4 times 1 is -4. Oh, shoot, we want it to be 9. What do you do to -4n so you get 9? You add 13. So you put in a 1, you get -4 plus 13 is 9. You put a 2 in, -8 plus 13 is 5. Easy. Or use the new formula we learned. A sub n equals a sub 1 plus n minus 1 times -4. Right? Now all you got to do is distribute that. Right? So you just distribute this through. So you get 9 plus -4n plus 4. You got -4n plus 13. So if you were bothered earlier by being able to figure out these nth term formulas, now you've got the nth term formula for you. That's what this new formula is. It's the nth term formula. Okay, well, I'm glad I threw that one in there because I wasn't going to do that problem because I thought, no, that's too easy. That's just first. I mean, but good thing. Because I was going to start with this one. Okay, so let's do this one. I was going to start with this one, then I remembered the whole quadratic formula thing. I thought, no, I better start a little slower. All right. All right, A1 is -14. Now, this could have been written in words, but I was getting lazy. You know, find which term is 76. If you have an arithmetic sequence, it doesn't say arithmetic here, we'll assume it, but most of the time in directions it'll say that. arithmetic sequence where the first term is negative 14 and the common difference is 3. Which term is 76? Hint, use this formula. Okay? You don't have to, actually, but we'll count on your fingers and toes. Okay, what do you got?
31.
31st term, right? So you got a choice. You can do it like Jack's doing, and you can just add on 3 until you finally get to 76. I'm sorry, Jack.
No, it's
Just keep adding on. Start at negative 14 and keep adding on 3 until you get to 76, right? Or you can just use the formula, right? This side is the nth term. We don't know what term 76 is. It's a term, so we can put it on the right side, or the left side. So over here, we put 76. Here goes the first term. Here, n, we don't know, but we know the common difference is 3. So we plug in all those things we need, and we solve for it. It's the 31st term. Or we can sit here and we can keep adding on 3, and we can keep going and going and count until we get there. Or you could also subtract. Remember, we talked about this, common sense. You're going to add on a certain number of 3's to go from negative 14 to 76. So what could you do? Just common sense, don't use a formula. What? Take 76, subtract negative 14, which is what? That'd be 76 plus 14, which is 90, right? That's how many 3, that's the total number difference in there. How many 3's is that? That's 33. So you're going to add on 33's to get to 76. Well, that means it must be which term? The 31st, because you're going to start at the first term and you're going to add on 33's. That's going to get you to 31. Okay, that's going to be the 31st term. So that's what I meant by just common sense. If you understand what an arithmetic sequence is, and you're adding 3 every time to get from negative 14 to 76, you can just subtract that. It's a distance of 90. That's going to take 33's to get there. So it'll be 31. But why bother with that when you got a nice formula you can just use? Okay. All right. Do this one.
Come on.
Oh, I made it easy on you. You haven't even read the problem.
I got this.
Good question.
Oh, I know what you're lying about. You had to write out 11. Sure, that's what it was. Yeah, I see.
I can't even count to 11. I get to 9, then I get 7.
Okay, what's first term?
5.
5. And what's second term? 10, 15, goes by 5s. What's the first thing you needed to figure out? What the common difference was. What the common difference was. How'd you get it?
You do both of the common difference.
What do you mean?
Well, there's.
What do you mean both of the common difference?
Subscript. And then, subtract the common.
So wait a minute. You're telling me you do this calculation right here?
Yeah.
You do 65 minus 20 on top, and then you do 13 minus 4 on the bottom. That is a familiar looking calculation. What is that? That's slope. That's slope. The outputs, the terms are the y's, the bottoms the x's. Okay? 45 divided by 9 is 5. That's what we just got been saying. D, the common difference, is like slope. But you wouldn't have to think of it as slope. You could just think of it as you're gonna go from 20 to 65. You're gonna go a distance of 45, and you're gonna do that over 9 terms. So each one's got to be 5, right? So once you know the common difference is 5, you can take away 5 this way, add on 5 that way to get to where you need to be. Okay? All right. Do this one. Set. Authority.
I'll throw it away. I got it.
Okay, here we go. Finish this one.
What do you mean by 2 and 9?
First term is 2, second term is 9.
Oh.
Yeah.
I feel like there could be more.
Okay, one way to do it is what?
The equation.
Use the formula, right? Another way is what?
Yes.
Write them up, right? Write it out. So if the first term is 2 and the second term is 9, what do you know? The next one's 16. The common difference is 7, right? So keep adding 7. It's only the 9th term, so why not? Write them out, right? Now, if that said the 110th term, not a very good strategy, right? But find the 9th term, you just write them out, okay? So it could look like that, right? So 2, 9, 16, 23, keep adding 7. Or we could do the formula. Now, what's the formula look like? Well, on this side goes the nth term. Now, in this case, we want the 9th term. So n is a 9. So we're looking for a 9 is what we're trying to find. A sub 9. So trying to get you to see the different ways you can use the formula, right? And finding the different unknown parts. So a sub 9 is what we're looking for. That's letting n be a 9. If n's a 9 right there, then n's a 9 right there in that formula. It's a sub n. That's the same n that's in the n minus 1. So then you just do this right here. But again, why does this work? Because if you go from the first term to the 9th term, that's 8 d's you're adding on. 9 minus 1. And so what do we got? We got 8 d's. 8 times 7 is 56. And we started with 2. And so that we should end up at 58. And then that would be the third way you can do it, would be just common sense. Okay, you figure out that the common difference is 7. You're going to add on 7. You're going to go from the first term to the 9th term. That's 8 D's you're going to need. 8 times 7 is 56. So starting at 2, you're going to add on 56, and you're going to be at 58. So you don't really. So if you want to know the 110th term, what are you going to do? You're going to add on 109 sevens, right? You're going to add on 109 sevens onto the first term. Right, and that's all the formula's saying. So you got the formula there, so you just plug in and use it. But if you just understand what's going on, it's not a hard calculation either. Okay? All right. So there's a story. It's got to be my calculus class. So supposedly, I don't know if this is really true, but a famous mathematician named Frederick Gauss. As the story goes, I'm not, legend has it, when he was young and a genius and in school, that his teacher told him to go sit in the corner. Yeah, sit. No. Go sit, because you're a genius. Go sit in the corner and add up the numbers from 1 to 100, thinking that this would keep him busy and then he would, stay out of trouble and so forth. But he was a genius, and he came back in like 5 seconds, and he had the answer, and was amazed. How do you get that answer? Okay, you got it. You got it. What can you do? 5,000. Boy, you're really close. Maybe you just multiplied something. Did you say 5,100? Yeah, no, it's close. What'd you do? What was your strategy? Yeah, 5,050. 5,050. How'd you do it? Kate, how'd you do it?
You add 1 to
No. Yeah, you could do that. Okay. Except the problem is.
You can just do, 101 times.
Yeah. So, in other words, what he did is he took 1 plus 100, which is 101. And then he took 2 plus 99, and that's 101. And then 3 plus 98, and that's 101. And so how many pairs like that will you have? You'll have 50 pairs. And 50 times 101. Well, 50 times 100 is 5,000. And then 50 times 1, if you do distributive property, is 50. So 5,050. And that was how he did it. Okay? Now, what that leads us to is you can do that you can use that same pattern to add up any arithmetic sequence. This is an arithmetic series. This is an arithmetic series. You're adding 1 each time, right? The terms are going up by 1 each time. So that makes it arithmetic with the D being 1. So if we were to look at this one right here, okay? If we were to look at this one right here, we could use that same exact, pattern. Okay, we're going up by 2's this time, right? But what do you get with 1 plus 19? 20. 3 plus 17? 20, right? This one would be 15. 5 plus 15 would be 20. So we would get 20, and how many pairs would we have? Well, we need to know how many terms we had, right? Well, how many terms are there here? How many terms are there? Now, how can we figure it out? We can count them in our head, because there's not very many, and it turns out there's 10. We can also use the formula. What would I put on the left side of my formula? What would I put on the left side? But some term, but I need to know, right? What term? What term you want to put there? What goes 19? I want to put 19. I want to know what term that is. I want to know what n goes with 19, right? I need to know what term that is. That'll tell me how many terms there are. So the last term. So I want to put 19 here. Then what would I put here? 1 plus n minus 1 times 2. See how that works? Over here, where a sub n goes, if we know what the last term or the nth term, we put that on the left side. So we put 19 there. So take away 1 here, we'd have 18. This would be 2n minus 2. We could add 2. We get 2n equals 20. We get n equals 10. So there's 10 terms. Okay, there's 10 terms. So we have how many pairs then? Oops, so that each pair adds up to 20. How many pairs do we have? we have 5, not 10, we have 5 pairs, right? We have 5 pairs. We have half the number of terms, right? So there was 100 terms before. Wait. Never mind. Keep it secret. Come back. All right, I sense there might be a little bit of misunderstanding on this whole idea of an nth term. So when we talk about the nth term, the n just stands for the number of the term. So nth term would be like 15th term or 14th term or 27th term or 100th term. So n is that subscript. So when we talk about the nth term, so like in this problem, 19, and you could say 17 is an nth term and 15 is an nth term. It is. It's one of the terms. And whatever n is would be which term it is. But we don't know, because of that gap in the middle, which one it is. If we want to know how many terms there are, the last one would be the one that would tell us how many terms there are, right? If this is the 20th term, then that means there's 20 terms. And that's kind of what we needed to know here. We wanted to know how many pairs there would be, and so we need to know how many terms there were. And so that's what makes 19 the nth term we're interested in. Right? And that's why I put 19 over here in this formula, where this says a sub n, where on the left side is the nth term. This is the first term. Here we put the nth term, okay? And so that's why we put the 19 there. And then whatever n we find here is what matches with that term. So when we found n is 10, then that tells us that 19 is a sub 10, the 10th term, okay? Just like in the previous problem where we found a sub 9. They wanted us to find the 9th term. So I put 8. We don't know it, so we just put a sub 9, but that allows us to put a 9 right there. Okay, anyway, we get half the number of terms because we're pairing them up. So there's 10 terms. You would have 5 pairs, and each pair adds up to 20. So 5 times 20, these numbers would add up to 100. So that gives us this formula up here, and it makes sense. If you look at it then, what do? We add the first and the last term, so that's what we did here. We take the first and the last term, 1 plus 19, gives us 20. That's what all the pairs will add up to. So we take the first term plus the last term, and then we multiply that by how many pairs we have. Well, how many pairs will we have? Well, it'd be the number of terms divided by 2. That's how many pairs we will have. So that's where this formula comes from, is this little Gauss, trick that Gauss used. And it works for any arithmetic series, okay? So any arithmetic series, we take the number of terms divided by 2, and we multiply it by the sum of the first and the last term. Okay, so notice that's S sub n, S standing for sum. So we have 2 formulas now that we've learned today. One is the formula to find the nth term, which is this formula right here. That's a sub n equals, so that's a formula to find the nth term of a sequence, and this is a formula to find the sum of n terms of an arithmetic sequence, or the nth partial sum. Okay, so 2 different formulas mean 2 different things. They tell you 2 different things. Okay, that's the sum. The other one is just to find a term. Okay, so do this problem here real quick. the word partial in there? Why did they say find the partial sum? We've said it a number of times, but I mean, we've talked about it a number of times, but why? Why the word partial? Because it's an infinite sequence. It goes forever. We're just saying, hey, stop at 150 and add up those terms. And so that's a partial sum because it's not all of the terms of the sequence, right? So that's why the term partial sum, okay? We easily could have said, find the sum of the first 150 terms, right? That would be saying the same thing, okay? But that's a phrase that would be more words, right? This says the same thing. And that's a term we use. Okay, what do you got? Somebody?
About 724.
No.
That's what
It's over 100,000. Oh, gosh, that's close. How did you get that close and not quite have it right? It's really close. 124,000.
I got 123,600.
There it is. Okay? Now, to use the formula that we just learned, what's missing? What don't you know then? The last term, the 150th term. Oh, gee, if we only had a formula to find the 150th term. Oh, do we have a formula to find the 150th term? What is the 150th term? 1644, right? So we need to find the sum of the first 150 terms. We need the first term and the last term, the 150th term. So we go to our nth term formula. We want the 150th term. So we do A1 plus n minus 1 times the common difference, which was 11, right? So here's an example where you would use both formulas. So we multiply it out. We get 1,644. Okay, so that's the last term. And so then we go to our sum formula. So first plus the last, and then n divided by 2. Right? So we got both formulas. So you want to use this, you want to add up 150 terms, you need to know the first term, you need to know the last term. You're either given the first term and the last term, or you've got to find the first term and the last term. Or maybe you're given the first term like this one, you got to find the last term. That's where the nth term formula comes in. So you got to use both formulas. So those would add up to 123,675. Okay? Try a similar problem. Now remember earlier hint I gave you, when you're given a sigma notation, a lot of times your very first job is to do what? Expand it out, right? That's where I would start probably. Okay. you got? Anybody? 3 digits. 292. Okay. Now, again, there's not very many terms. How many terms are there when you expand this out?
8.
There's 8 of them, right? 15 minus 8 is 7 plus 1. We were talking about that earlier, right? Some of you may have gotten thrown off because I started that with an 8. You shouldn't get thrown off. That doesn't matter. That just generates the sequence for you. So you start I at 8. You plug in an 8. You get 24 plus 2 is 26. Okay? And then you plug in a 9. And then you plug in a 10. And then you plug in 11. And when do you stop? After you plug in a 15. Right? That's 8 terms. Now, on a quiz, if I wanted to make sure that you use the formulas and don't just add them up on your calculator, I'm going to give you way more terms than that. I'm going to go from 8 to 179 or something like that, right? Because, so I said, where you would normally start with something like this is expanded out. So, put in an 8, put in a 9, a 10, an 11, a 12, a 13, a 14, and a 15. 1, 2, 3, 4, 5, 6, 7, 8 terms, right? But if I wanted you to not be able to write them all out or not take the time to write them all out, I would go from 8 to 179. Then you would do this. Because all you really need to find the sum is what? The first and the last. All you really need is the first and the last. And to know how many terms there are. Right? So all I needed to do was do 26 plus 3 is 29, or, just put in the first couple, dot, 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 and then do the last. And how do you get the last? Put in a 15, right? So if this signal went from 8 to 179, you would put in an 8, that'd give you the first term, put in 179, that'd give you the last term. That's all you really need to do the sum, is the first and the last. Okay? And you need to know how many terms there are. So if this was an 8 to 179, how many terms is that? From 8 to 179? 179 minus 8 is 171 plus 1. So there'd be 172 terms, right? That'd be 172 terms, and that'd be your end. So there you go. So you go to the formula, but again, you can write it out, but you don't really need all those terms. But like I said, there's 8 of them. You could just get in your calculator and add up all 8, right, if you want to do that. If you didn't want to use a formula, right? But I would maybe make it more than that, so you would be tempted to use a formula. Or I may just say in the directions, use the sum formula for an arithmetic series, and then I want to see your work. Okay? And so then it comes out. So you have the first term and the last term. There's 8 terms. Now don't worry that this is 8 and this is 15. You might be saying, well, that's the 8th term and that's the 15th term. Sure, maybe we're looking at the middle of some sequence, but all I want to do is add up this sequence. So I'm going to call that the first term, and I'll call that the 8th term. Even though that was an 8 and a 15, that part doesn't matter. Okay, that part doesn't matter. It's still the same sum, right? If I take those 8 numbers, and they're in the middle of some sequence, and I want to add them up, that's the same sum as if they were at the beginning of the sequence, right? So you can that's why it's called a partial sum. It's just that part, those 8 terms. Okay. Real quickly here, you don't need to write anything down for this. This is a section of the book. I'm not going to sign it. We'll just do it together real quick. So all this says is determine whether this sequence is arithmetic. Yes or no. If it is, what is D? Okay? Yes or no?
Yes.
What is D? Negative 2. And remember how you do that. 8 minus 10, 6 minus 8, 4 minus 6, negative 2. Okay? Yes or no?
Yes.
And? 5. No. No, you're dividing by 2, right? See, this is where that subtracting thing comes in handy. So you have your calculator, so subtract. So this is 8/4, right? What's 8/4 minus 9/4? Negative 1/4. What's 7/4 minus 8/4? 3/2 is 6/4. 6/4 minus 7/4. Now, if you're using your calculator, you don't even need to do that, right? You can just go 2 minus 9/4, negative 1/4. 7/4 minus 2, negative 1/4. Just subtract. Oh, yeah, negative 1/4. Okay, so that's D, negative 1/4. Okay? Negative 1/2. 5/2 minus 6/2, that'd be negative 1/2. 3/2 minus 4/2, negative 1/2. Okay? Yes? 0.6. Yes? 0.4. Now, what do you do? ln2 minus... What's our law of logs that would apply right there? You can write that ln 2 over 1. Okay, well, let's check. What's ln 3 minus ln 2? That'd be ln 3 halves. That's not the same as ln 2. So the answer is no, right? So you gotta be a little creative. What about this? No, that'd be 4 minus 1, that's 3. This would be 9 minus 4, that's 5. So the answer would be no. Okay. There you go. Everything you ever need to know about arithmetic sequences and series. 2 formulas that you will use, can use a lot. And you should practice using them, even though, like I said, common sense, and you can figure out some of that stuff. But I may on the quiz, say, especially if I give you the formulas, may say, use the formula and show your work, just so we, get comfortable using it, are familiar with it. It'll be even more important, I think, once we get into the geometric sequences tomorrow, which is when you multiply each term to get the next term.
I can't. Oh my God, Mr. Clarkson. Good job.
He said he's going to.
Bro, I still have been able to eat your hand.